Um, if you think it is okay, we can start right now.
It's up to you totally.
Okay, I would like to start with opening conservation. Welcome again, everyone. Today, our second instructor is going to be Duygu Altınok, who is senior NLP engineer in DeepGram. She will present a work titled From Vectors to Decoder-Only Models, How Generative Models Reach the Top.
Hello, people. Yes, so I'm going to just share the screen. Hope it's off. You see the screen. So today is actually sort of a snapshot of my new documentary. So today's documentary subject is how the generative AI reached this point. So topics is as follows. At the end, we would like to reach to the point, what is a decoder-only model? And in order to reach this point, what we would like to do is that we want to just investigate some building blocks that and also to understand the underlying ideas behind the decoder-only model. So we are going to start with very, very simple notions that what is a neural network indeed. Then we are going to slide to the word vectors and LSTMs, like the basic building blocks of NLP. Then we are going to slide to the transformers, attention mechanism, and then we are going to finally reach the decoder-only models. So first of all, what is learning? Learning is about the approximating the function that produce your data. So if I give you these pairs and ask you to just guess what is the function that generated this distribution, you can find it easily. It's this one, x to the x squared. However, when you have more data, and indeed you have more dimensional data, it becomes complicated quickly. And if I ask you, what is the function that generated this data distribution? That's a bit difficult to find. And I'm not going to say it because I generated something, a random polynomial, but I forgot the weights. So indeed, I don't know it right now. But it was something with 2 times x squared minus 3x and some thingy. And coming to the neural networks, what do they do? So if you remember the previous slide, you have some points and some values, and you want to just learn the function that generated this distribution. That is exactly what neural networks do. When the function is quite complicated, you want to estimate it. So neural networks just learn functions that generated some data, and the function is usually quite complicated, and that's why we use some complicated and layered thingies that can approximate this function. During the learning, what you do is this. You want to estimate the weights within each cell. So you throw the inputs, and you start with some random weights, and you know the output already, that what should it be. And after, with the random weights, you calculate an output and compare it to the idealistic output. And when you do this iteration many times, at the end, you approximate the weight and get meaningful values here. So how it just goes to the NLP is that we want to work with words. So as you see, everything is just number. So per word, you need some numbers, some vectors. Very beginning of the early NLP days, there were these ideas how to vectorize the words. So very basically and not very intelligent idea was sparse vectors indeed. So when you look at this one, what you do is usually you sort all of the vocab words like this, and then you give numbers to the vocab items. Then you do a one-hot encoding. You put a 1 to the position of this number, just like it. You put a 1 to the 205th position, and the rest should be just zeros. But if you look at this approach, you see it's not very feasible, because when you have a bigger vocab, you will waste a lot of space. Second time is that the vector length is not very guessable. If you want to add new words, then you need longer vectors and you need to change and retrain your algorithm. That is bad. And moreover, the most important thing is that if you have such related words, they are not related anyway. So semantically, there is no relation between these three words at all, or just these two words. It is just some randomness in the vocabulary. So, and then comes the next idea that can we do it more intelligently? So per each vector for the vocab item, can we do it such that the vector length is fixed? So we know it already. And for every vocab item, we also want to have something meaningful that for some words, we can just model the semantics, just like in this one. So for these words, we want to model the gender in some dimension, and being a royal or a normal people. Maybe if the word is a verb, it is plural, singular, human, animal, or something else. And this vector should also have some good capabilities such that when we want to use that with vectors, they should look meaningful, just like this. So the answer to this call is called word vectors, which happened and which was, I would say, came out by the 2013, 11 years ago. And I would say that was the starting point of the modern NLP. So this is called a word vector, and a word vector is just really a vector, just like it, that every word is presented as a dense vector of a fixed size. Size can be 100, 200, or 300. It depends on who trained it. And how we trained and get such vectors is that you have a network like this. We will come to it again. And what you would like to do is that you want to give some context words and the surroundings to the algorithm. So here, the input, you can do it in two ways. Either you give the middle word and give a context of 5 words and ask the algorithm to guess the input, so which is the middle word. Or you can give the middle word and ask the algorithm to guess this one, surrounding, which is context. And this is from the original word2vec paper. Here it is. You give the context words, surrounding words, and just guess the middle word. Or vice versa, you give the middle word and ask the algorithm to guess the surrounding word. So it is called continuous bag of words and skipgram. By the way, 2 algorithms that consist of word2vec. And how you train this algorithm is that you throw a lot of text, huge amount of text, and then train it. Just like NLP today, word vectors also included huge vectors of text. And also in oncoming time, we will always see huge amounts of text anyway. So word vectors also introduce transfer learning. Here is what happened. Some big companies such as Google, Facebook, and some other companies pre-trained word vectors on their corpus, packaged them, and put them to the internet, and you downloaded them. So word vector packages just really looked like this, some arrays written to a file, and when you want to use them for your algorithms, you just take them and use them. And this is called transfer learning. So in this setup, word vectors represent the inner structure of the language. And whatever the downstream task is, that such as classification or other algorithms, you just take this info about the language, take it, and then apply to your data. So very good. We have some now word vectors, but then they are sophisticated. We need to put them into some sort of models that can model sentences, and that comes to LSTMs. So the very first, I would say, great NLP model is actually LSTM. Before LSTM, there were some sequential models, maybe conditional random fields, but none of them were successful as LSTMs. Okay, so LSTM is called long short-term memory models. And here, I don't know if you are scared by the shape, but don't be. What you would like to do is this. For sentence, just like this one, for each time step, you would like to input 1 word. And you would like to input your sentence word by word. So at the time step 1, you're going to feed this. and the step 2, you're going to feed this, and the step 3, you're going to feed this. At the very end, first of all, at each step, you are going to get one vector, which represents semantics of this step and this word. And also at the very end, you are going to get an encoded version of this sentence, which is called the encoder representation. So before that, we come to this once more again to see what does encoding mean. What happens inside this LSTM is actually a lot of gates. So one is called forget gate, other is called forget gate, other gates, and quite many gates actually. But what you see is here, if you look at carefully, LSTMs has an inner memory. What it means is that when you feed the words one by one, LSTM remembers some information, forgets some information, and keeps some information somewhere inside it. Usually it is shown as H, which is the hidden vector inside, and also the output of each step. Okay, people, so it looks actually very convenient because sentences goes one by one, and you would like to go from left to right in quite many languages. Of course, you can't go from left to right either. So what does this do actually? When we come to here, encoder, this is the aim of this LSTM. You want to encode the sentence. You want to get one vector which represents the sentence. In order to do that, you need to feed and show all of the words to your model. This is called encoding. And LSTMs are encoders, which is great. So question. So here, once more, encoding is to generate vector from text, and reverse is to decode. So what is a decoder? Decoder makes vice versa, get a vector and generate the text. So here is the quick question. If we can use a LSTM with an encoder, can we use it as a decoder? Surely yes. Here what happens is that you want to generate some text. Actually, you want to do a machine translation. Here, how it goes is as follows. You, again, feed your input sentence one by one. And at the end, you get a vector called context vector, which represents this sentence. Then you want to feed this sentence, this context vector, to the decoder, such that from this context vector, decoder should start generating some words. So here is how it is happen. At the beginning of the generation, you put a token, either start of the sentence or start something specific, which signals the LSTM, the decoder LSTM, that you are going to start generating. Then you generate something. And then you take this output and input to the LSTM again. Then you take something else, you generate second one, then you feed this, you feed this, and then you generate this token, which is end of sentence, which means stop here. So this is a, I would say, special token also. So here notice that encoder and decoder have different vocabularies. One is called the source language that you encode, and the decoded language is called the target language, at least in the neural machine translation. And what happens inside LSTM is that it is just like here. When you decode, you feed the words, you get a vector. And that vector, in each step, you just map it to a vocabulary word, which is very good. So did we generate some text? Certainly, yes. Is this a generative model? Definitely, yes, because we did something. We generated some text. And one more thing is that we fed to this model decoder the input of itself. And that is called the autoregressive modeling, that you feed whatever you generated from steps. And now comes one more idea, which happens to be the attention. So if you just think about this example here, when you generate this one, étudiant, most possibly, all of the words are of course related, but some of them are more related. Here, étudiant is just a one correspondence of student. And when you want to generate share, you would like to look at this one. So this is sort of, some words are more related to some input words, and you would like to model them. Some words have more attention and importance while generating some other words in the target vocab. So this is why the attention mechanism is indeed invented. So in this mechanism, what you do is that you prepare a rectangle of weights which shows that which input word is related to the which output word. And when you output some words, that when you decided to output which word, you look at these weights and you pick the input, you look at the input words that are more related. This is called attention mechanism. So everything looks so great, but what are some shortcomings? So first and very important shortcoming of LSTM, I would say, is to fail to model long dependencies in the input text. Remember, we feed the words one by one. And then, so I wrote this example passage for you. When you feed everything one by one, after some point, especially in the long text, LSTMs start forgetting the previous information. So when you come to the here, that there is a here, and most possibly LSTM already forget about who is he refers to. John is just much before. That is sort of a problem actually. And there is a second problem related to this issue, long input, which is just numerical instabilities. If you run these loops for a long time, then I would say numerical methods become very fragile. Gradient calculations just become problematic. That's a related problem. Another computational problem is that you need to feed everything one by one. Then there is no room for parallelism. Even if you have GPU and computing resources, you cannot use directly them because you need to feed words one by one. There is no parallelism in this business. And another more important issue is that if you have all of these, such as some typos like this, and also some rare words, most probably word vector lookup is going to fail. Because, as I told, word vectors is a static file, and you'll use static word vectors. So if you have a typo like this, you are not going to find it in the word vector file. So this, if you see this word, your LSTM will start with random weights, which is going to hurt the performance. Another issue is rare words. Even if you know the words separately and there is only one tiny character in between, this long word is not going to match anything. So it will start as an unknown word on the training, and during the test time, your algorithm is not going to recognize this. So as an answer to all of this, before that, what we learned so far. First of all, we learned how to densely represent words with embeddings. Then we saw the idea of transfer learning. Then we saw encoding and decoding. What are those and how we do that? A bit of autoregressive modeling and attention. In order to fix the shortcomings of LLMs, transformers came out. And transformers just collected all of these ideas, but in a tiny bit different way. So if you just look at transformer as a black box, I don't know if you see this picture before. This is actually like the, I would say, summary of what transformer is. So transformer model, this is an encoder. You feed your sentence like this. Please skip this one for a minute. And you would like to get a sentence vector, so an encoded version of your sentence. And also possibly you get word vectors per each. And then that's it actually, but you would like to do in an intelligent way, more than LSTMs. So first idea to make it more intelligent than LSTMs is that to change the vocabulary a bit. So the not recognized words go away. How you do is this? You do it with different transformer tokenizers. So here is an example that this word's rumination is divided into two shorter words. But the other words, which are most likely to be in the vocab, is preserved as is. This is a transformer tokenizer. So transformer tokenizers take the word and just split them into parts. And if you see this sign, it means a part of word. It means the splitted continuation of another word. And word vectors are just word vectors. There is a fixed size that each word produces a vector, and also to the sentence. Okay, so how does transformer work? Transformers are like this. Okay, first left side, please. When we look at from a very, very distant place, transformers look like this. You give your sentence, and there is an embedding here to apply to each word. Then there are encoder blocks, just like LSTM. First, you encode your sentence. Then, this is for machine translation again. You have a target, which is what you translate. Let's say English to French. And same thing happens to the target sentence. This time, you feed the target to the decoder blocks, but also decoder blocks can see the result of the encoder blocks. Then you generate your output. If you have a more closer look to the encoder, you see in each encoder block two tiny mini blocks, I would say. One is self-attention and other is feed-forward. Feed-forward is just one layer network, and coming to the decoder, you see a self-attention and the decoder-encoder attention. So one of the most important ideas of the transformer is self-attention. So that comes in the next slide. Come on. This is what is called a self-attention, that every token in the input sentence attends to every other token in the input sentence. So what does it mean? Remember, to the LSTM, we just show each word one by one. Here, in this, I would say, outlook, every input word can see the other word. So you process the sentence as a whole. Every word sees each other. And as a result, this is actually, I would say, you can also model the long-term dependencies better because everyone sees each other at the same time. Also, if you remember, another problem with parallelism, here this is if there is tricky and I would say efficient ways to do parallelize this. So this everything here in these blocks you can run in parallel. So self-attention is actually answer to more than one thing, both parallelism, efficiency, and also modeling the long-term dependencies. So if you look at this one again, sometimes you do not need to generate output. You just want to represent your input and just encode your sentences. Then you use only this one, encoder block. Some encoder-only transformers, all of them I think very famous, BERT, Electra, Roberto, and XLMR, and BART and T5 are usually used for neural machine translation. They have both encoder and decoder. After that, I think we can come to now generative AI, which is decoder-only models. So most of the models that you see as generative AI and LLM are decoder-only models. So decoder-only model is actually this block, decoder block, multiplied and stacked many times together. Only tiny differences here because there is no encoder, so there is no encoder and decoder self-attention, actually. So a decoder block looks like this. Tiny detail, this is called mask self-attention because when you decode, you can only see and you generate the words one by one. You can only see whatever you generated so far. You don't see the future. So in the computations, you just, in the training phase, you mask the feature. That's it actually. Whatever that is called generative AI is decoder layers. And how they work is as follows. it is very similar to the transformer. You start with words. Then you feed it to the decoder. Here, input to the decoder on the models, as you know, is called a prompt. So prompt is your starting sequence. Let's say this is your starting sequence. You feed all of this. And after you feed your prompt, then text generation start. Here, after this one, we see this word, and then we generate this word, the. And at the next step, we feed it to. So there will be 5 words, which is fed to the network. Then we generate next one, wrote. Then we feed it, and we get an end of sentence. So it means to stop generating. That's it actually, nothing fancy. And this is also, if you remember the generative LSTM, this is also autoregressive model, right? Whatever you generated in the previous step, you feed it again. So decoder-only models are autoregressive models also. As you remember, and if you remember from here, most of the ideas in NLP so far just go around these ideas. How to encode the sentence in the best way, and when you generate, how to decode in the best way. And when you when you pre-train the transfer networks, you put them onto Hugging Face or another place so that people can just use them on their tasks. So it is transfer learning. Autoregression modeling, yes. Whatever you generate, we feed it to the model again. And attention, yes, in different ways. Either an encoder, decoder, between the encoder and decoder. So as you say, I would say there is a handful of ideas. But however, and whatever, in the which way you implement them and offer them is actually matters. That is why transformers created the evolution. So here's some decoder-only models that I know the parameters 100%. GPT-3 is like the ancestor of GPT-3, and it was trained on 4 GB of training data, which is sort of humble, and 1.5 billion parameters needs to be trained. And in the next epoch, GPT-3 is trained on a huge text, like 570 GB, many, much more parameters. And another idea is to, I think, to make the GPT-3 has more blocks than GPT-2. So as you see, the trend is to make the model bigger, more parameters, but you also throw more data so that the model learns better. So this way, I think paradigm of these days, as at least generative AI, is to put more data and make bigger models. So that's it actually. This is just evolution of NLP in 30 minutes. And I just want to say, in my YouTube channel, I'm going to offer 2 documentaries, longer versions, most probably 1 to 2 hours. It will be in 2 languages, both Turkish and English. It will be in my channel, YouTube channel called NLP with Duygu. And if you want to follow my work, please follow me on LinkedIn and YouTube. That's it from me. Thank you for joining. If you have questions, I can just pick them.
Is there anyone who has questions? Can I ask you in Turkish something?
Yeah, sure. Türkçe de olur tabii ki.
Hocam ben sizi biraz araştırdım gelmeden önce de bilgisayar mühendisinden ODTÜ'den mezun oldunuz değil mi?
Evet.
Sonra matematikte ilerlemeyi tercih etmişsiniz galiba akademide.
Çok sayılmaz aslında. Master'ım uygulamalı matematik. 2 yıl biraz da uygulamalı olasılık teorisinde vakit geçirmek istedim ama PhD'm kombine bir program. PhD'm Computer Science, Combinatorics ve neydi diğer şey? Probability miydi? Üçüncü bir şey vardı. Gittiğim programın adını unuttum. PhD'm kombine bir program. Hem Computer Science var, Machine Learning var, uygulamalı matematik var, Numerical Algorithms var. Ama evet, matematikte de bolca vakit geçirdim. Doğrudur.
Ya hocam şeyden sordum. Ben de matematik öğrencisiyim. Kariyerime hani akademik açıdan mı devam etmeyi düşünüyorum yoksa bu tarz işte yapay zekadır, NLP'dir falan karar veremedim. Daha birinci sınıfım zaten de. Size de bir fikir almak için sormuştum.
Şöyle söyleyeyim. Yani ikisini yapan taraf, yapan insanlar, ben ikisini de yaptım. Ama ben önce akademi hevesiyle başladım. Hatta master'dan sonra PhD'ye çok hevesliydim. Sonra PhD'nin birinci yılında aslında yaşamak istediğim hayatın akademik hayat olmadığına kanaat getirdim. Yani bana çok uygun olmadığına kanaat getirdim ve sıkılmaya başladım. PhD'm de uygulamalıydı ama yapmak istediğim kadar kod yoktu. Ve bu beni birazcık sıkmaya başladı. Sanırım o kişiden kişiye göre değişiyor. Yani çok hevesli başlasa bile bazen insan akademiye kendine uygun olmadığını sonra anlayabiliyor. Şöyle söyleyeyim, bunun bence fix bir formülü yok. Yaşayıp bakmak gerekiyor. O yüzden şöyle tavsiye edeyim, mümkünse ilerleyen yıllarda ve mezun olduktan sonra birazcık çalışmak ve yaz stajı tavsiye edeyim. Girip ben olsam girip bakarım yani. Endüstriyel işler nasıl, akademik işler nasıl? Naçizane tavsiyem.
Tamamdır hocam. Çok teşekkür ediyorum tavsiyeleriniz için.
Rica ederim, bol şans dilerim.
Sağ olun.
Özellikle akademik yolu seçenlere Allah'tan sabır diliyorum.
Biraz öyle olacak gibi gözüküyor. Şu anlık matematiğe fazla tutkulu gibiyim. Bakalım.
Yani yapıp mutlu olan arkadaşlarım da var tabii ki. Biri benimle yaşadı. Şimdi ODTÜ'de hoca. Amerika'ya gitti PhD'ye, Rutgers'a. Çok tutkuluydu. Hala da çok tutkulu. Adam mutlu hayatından.
Çok güzel. Teşekkür ediyorum tekrardan.
Rica ederim. Başka soru varsa kapayım. Yoksa kaçabilirim. Sanırım başka soru yok. O yüzden ben de sunumumu bitirmiş oluyorum. O yüzden kaçıyorum kendimi sessize alıp.
Çok teşekkür ederiz tekrardan
Rica
katkılarınız için.
ederim.